Calculus Video 61, L'Hopital's Rule, Examples 2. Or maybe a better title for this would be L'Hopital's Rule for Limits that are not 0 over 0 or infinity over infinity. So the question is, what if I have this limit? As x approaches a, which may be 0 or infinity or some other number, right? The limit as x approaches a of my function does not equal 0 over 0 or infinity over infinity. But it's instead some other indeterminate form. And you might be asking, okay, well, what other indeterminate forms are there? Well, there's lots. Here's a couple other examples of indeterminate forms, like 0 times infinity. What is 0 times infinity? Is it 0? Is it infinity? Is it something in between? Okay. How about infinity minus infinity? Well, that might depend on which infinity is the larger infinity. Or how about 1 to the power of infinity? What's 1 times 1 times 1 times 1 infinitely? Well, that might depend on what 1 is. Is it exactly 1? Or is it just a smidge above 1? Or a smidge below 1? Or how about infinity to the power of 0? We always say anything to the power of 0 is 1, but what if that number is so big it's going to infinity? If you take that number to the power of 0, is it still 1? These are all examples of indeterminate forms that we just can't exactly find the answer to, but they're not 0 over 0 or infinity over infinity. And only those two forms, 0 over 0 or infinity over infinity, only when we have those two forms can we use L'Hopital's rule. So we cannot use L'Hopital's rule on these other indeterminate forms unless we rearrange it first. Okay? If we rearrange the function so that it's no longer like 0 times infinity or infinity minus infinity or one of the other indeterminate forms, but if we can rearrange it so that it is 0 over 0 or infinity over infinity, then we can use L'Hopital's rule. So that's what we're going to work on today. I have a couple of examples about functions that are in some other alternative indeterminate form like this, and we want to rearrange them so that they're 0 over 0 or infinity over infinity. So let's start with this example here. All right. Again, like always, let's just do some direct substitution. Let's plug in the 1 coming from the right-hand side. If I do direct substitution, I get 1 over 1 minus 1 minus 1 over the natural log of 1. That would be 1 over 0. Minus natural log of 1 is 0. That's 1 over 0, which is 1 divided by 0 is infinity, and 1 divided by 0 is infinity. Infinity minus infinity. Okay? Is that 0? Maybe. Is it infinity? Maybe. We don't know, which is why we call it indeterminate. In fact, the answer here might not be 0 or infinity at all. It might be just some number, like 7. So we need to find out. In order to, say, use L'Hopital's rule, however, we can't use L'Hopital's rule right now. And we'll check it out at the end. We'll try it and show that it doesn't work. But for right now, we need to rearrange this function, this 1 over x minus 1 minus 1 over natural log of x. We need to rearrange it. We need to do some algebra in order to get it into like an f of x in the numerator and a g of x in the denominator, right? We're trying to force it into this form, where we have an f of x divided by g of x with the goal that it's either equal to 0 over 0 or infinity over infinity so that I can use L'Hopital's. Right? We're trying to go from here into this form. And the only way I can see to do that right now is to go ahead and get common denominators and combine those fractions. The 1 over x minus 1 minus the 1 over natural log of x, get common denominators, put those together. So let's try it. This is equal to the limit as x approaches 1 from the right. Common denominator would be x minus 1 times the natural log of x. That means the fraction on the left here would need a natural log of x top and bottom. Right, something like that. And the fraction on the right would need an x minus 1 top and bottom. Something like that. Okay, now let's go ahead and put those fractions together to get the limit as x goes to 1 from the right of the natural log of x minus negative 1. So it'd be minus x plus 1 over x minus 1 times the natural log of x. So it's the limit of that whole thing. Now that we've rearranged it to I have a function over a function, the f of x over g of x, let's re-plug in the 1. We'll do a redirect substitution and see what we get. So we get the natural log of 1 minus 1 plus 1 over 1 minus 1 times the natural log of 1. Okay, the natural log of 1 is 0. Minus 1 plus 1 over 0 times 0. Right, 1 minus 1 is 0, natural log of 1 is 0. So in my numerator I get 0, in my denominator I get 0. Now we are in a form, an indeterminate form that we can use L'Hopital's rule on, 0 over 0. So this limit that we have up here, which looks complex, we'll do L'Hopital's rule on this. Because we now are in 0 over 0. So this is equal to, don't forget the limit. The limit as x approaches 1 from the right. And we'll just take the derivative of the numerator and the derivative of the denominator. So in the numerator I have the natural log of x. Its derivative is 1 over x. Minus the derivative of x, so that's minus 1. And then the derivative of 1 is 0. In the denominator, however, that's a product rule. So let's do product rule. The derivative of x minus 1 is just 1. And we leave the natural log of x. Plus, we leave the x minus 1 and multiply that by the derivative of the natural log of x, which is 1 over x. Let's see if we can simplify here. We have the limit as x approaches 1 from the right of 1 over x minus 1. Natural log of x, and if I distribute the 1 over x into both the x and the negative 1 here, I get 1 over x times x, that's just 1. 1 over x times negative 1 is negative 1 over x. Okay, so that is L'Hopital's rule. That's the derivative, a little bit of simplification. Now, again, direct substitution. Don't go right into L'Hopital's rule again. You got to always do direct substitution to see if you get something. If I plug in 1, I get 1 over 1 minus 1. Natural log of 1 plus 1 minus 1 over 1. That would be 0 on the top, and natural log of 1 is 0, plus 1 minus 1 is 0. Okay, so 0 over 0 again. That means we're doing L'Hopital's rule again from this guy right there. So once again, L'Hopital's rule says that is the limit as x goes to 1 from the right. The derivative of 1 over x, we talked about this in the previous video, that is negative 1 over x squared. We use that one a lot, good one to know. Minus 0 over the derivative of natural log of x, that's 1 over x. The derivative of 1 is 0. The derivative of negative 1 over x squared is positive 1 over, the derivative of negative 1 over x is positive 1 over x squared. All right, once again, let's plug in 1. When I plug in 1 this time, I get negative 1 over 1 squared minus 0 over 1 over 1 plus 0 plus 1 over 1 squared. That is negative 1 over 1 plus 1. That's negative 1/2, and we have found our answer. In this case, oddly enough, the infinity minus infinity, negative 1/2. Probably didn't see that coming. But if you looked at our original function, 1 over x minus 1 minus 1 over the natural log of x, and look to see what would happen as x approaches 1. There's a hole in the graph at 1, but as x approaches 1, the y value there is getting close to negative 1/2. All right, very good. So it didn't start out in 0 over 0 or infinity over infinity form, but we did some algebra to rewrite it in a form here that was 0 over 0, so that we could use L'Hopital's rule. All right, let's try one more of those. Actually, I promised you. What if we tried L'Hopital's rule from the beginning? In other words, what if we didn't put it into the 0 over 0 form or infinity over infinity form, but we just have the infinity minus infinity form? We just had from the very beginning the limit as x approaches 1 from the right of 1 over x minus 1 minus 1 over natural log of x. What if we just did L'Hopital's rule here? Right? And I just took the derivative of 1. So L'Hopital's rule here, the derivative of 1 is 0. The derivative of x minus 1 is 1. The derivative of 1 is 0. The derivative of natural log of x is 1 over x. And if I were to now do direct substitution, plugging in 1 for all the x's, I get 0 over 1, that's 0, minus 0 over 1, that's 0, that's 0 minus 0 is 0, which is not the right answer. Our right answer was negative 1/2. So just to show you that you really have to put this into 0 over 0 or infinity over infinity for these things to work. Not correct. That's what happens. You get the wrong answer. All right, example number 2. Let's say we have the limit as x goes to infinity of x squared times the natural log of x plus 1 over x. Okay, let's go ahead and plug in the infinity direct substitution and see what we get. We have x squared, that's infinity squared, that would be infinity, times the natural log. If I plug in infinity, I get infinity plus 1 over infinity. Okay, let's think about that for a minute. If x is going to infinity, it's getting bigger and bigger and bigger. A million. A million plus 1 divided by a million. Is adding the 1 there really making any difference as x is going to infinity? It's not really. Whether you have $1,001 versus $1 million, that's basically the same thing. As x goes to infinity, x plus 1 over x limits to 1. So what we're basically saying here is this is the natural log of 1. But the natural log of 1 is 0, and we get infinity times 0. Okay, what in the world is infinity times 0? Well, that's a good question. That's what we call it, indeterminate form. Could be 0, could be infinity, could be negative 2. Not really sure. Maybe pose a guess. What do you think it's going to be in this particular case? Is it going to go to infinity? Is it going to go to 0? I will find out. Okay, can I use L'Hopital's rule? No, I can't. I can't use L'Hopital's rule unless it's 0 over 0 or infinity over infinity. This is infinity times 0. So what I have to do is I have to find a way to rearrange this function, x squared times the natural log of x plus 1 over x, in order to make it into infinity over infinity or 0 over 0. Okay, well, give it a shot. Pause the video, take a few minutes, see if you can figure out how to rearrange this into a 0 over 0 or infinity over infinity form. Okay. Let's give it a shot. I'm going to take this x squared here, and instead of having x squared times the natural log of x plus 1 over x, I'm going to take that and move the x squared to the denominator as 1 over x squared. All right? It's going to look something like this. The limit as x goes to infinity of the natural log of x plus 1 over x over 1 over x squared. Remember that if we divide by a fraction, that's the same thing as multiplying by its reciprocal. So dividing by 1 over x squared is the same as multiplying by x squared. So I haven't changed the problem. But now when I do direct substitution and I plug in infinity, we get the natural log of 1 which we know is 0, and 1 over infinity, which we know is 0. And you get 0 over 0. And so now we can use L'Hopital's rule. Okay, let's try it out. That is the limit as x goes to infinity. The derivative of the natural log is u prime over u. And let's see, let's do u prime, sorry. The derivative of x plus 1 would be 1 times the denominator x minus, leave the x plus 1 times the derivative of x is 1 over x squared. That's the u prime. Over u, which is x plus 1 over x. That's my entire numerator. Divide that by the derivative of 1 over x squared, which would be, it's 1 over x squared, remember, is like x to the negative 2. So the derivative of that would be negative 2x to the negative 3, or negative 2 over x cubed. Now that's a lot going on here. Let's see if we can simplify this a little bit. So in my numerator of all numerators here, I have x minus x plus 1. So that would be the limit as x goes to infinity of x minus 1 over x squared over x plus 1 over x. But instead I'm going to write that as times x over x plus 1. Put a little side work over here for that. Divided by negative 2 over x cubed. Basically I'm taking this fraction here and multiplying it by its reciprocal to become x over x plus 1. Okay, now it's looking a little bit better. The x minus x up here cancel out, and I just get negative 1. The x here cancels out with one of the x's there. And if I have, simplifying that, I get the limit as x goes to infinity of negative 1 over x times x plus 1 divided by negative 2 over x cubed, which is times x cubed over negative 2. Okay, let's see, the negatives cancel. We get the limit as x goes to infinity of x cubed over 2x times x plus 1. Or if I multiply that out, that's the limit as x goes to infinity of x cubed over 2x squared plus 2x. All right. Now again, if I could plug in infinity over infinity here, infinity in each case, I'd get infinity over infinity. That's L'Hopital's rule. I could use L'Hopital's rule, or I could go back to growth rates. I know by growth rates that as x goes to infinity, that a degree 3 polynomial will grow faster than a degree 2 polynomial. Therefore, as x goes to infinity, this thing is going to go to infinity. In this particular case, infinity times 0 is infinity. But please don't think that infinity times 0 is always going to be infinity. It depends on the particular functions that were given here. If we just switch this from an x squared to an x, right, so instead of x squared here, I just put x, that's still infinity times 0, but the answer is no longer infinity. It's something different. Try that one on your own.